Our project is production of activated carbon by process of rice husk.
I'm Richard Faxon. Our school is State Boarding School for Gifted Children named after the Parliament.
Rice is an important staple food for 3.5 billion people on the world. According to Food and Agriculture Organization of United Nations, in 2015, the yield of paddy on the world reached 749.1 million tons and it will tend to increase in the following years. According to statistics, rice husk, a byproduct from the milling process, made up about 20% of the weight of paddy. Thus, the annual generated rice husk is about 150 million tons. Activated carbon is a well-known material used in ever-increasing numbers of environmental applications, environment protection, water and wastewater treatment, and gas filters. Activated carbon can be produced theoretically from any carbonaceous material rich in elemental carbon. Agricultural byproducts available in large quantities are bagasse and rice husk. The annual global production of 800 million tons of sugarcane results in 240 million tons of bagasse, while the estimated annual world rice production is about 571 million tons, resulting in approximately 140 million tons of rice husk available annually for utilization. Recently, the use of activated carbon has increased rapidly. Resource base of activated carbon is quite varied, from crop waste to lignite and coal. Activated carbons obtained from these resources have high ash content and low mechanical strength. In addition, the inventories of these raw materials are reduced over time. Therefore, finding an alternative sources of raw materials for the production of activated carbon is an actual problem. However, using rice husk to produce activated carbon is significantly cheaper than other precursors. Production of activated carbon from rice husk has been the subject of many studies. However, these studies failed to demonstrate the efficient way to utilize a significant amount of amorphous silica dioxide, which is contained in the ashes. This work is dedicated to the production of activated carbon from rice husk in Turkmenistan. Production of activated carbon from rice husk in Turkmenistan is carried out in 3 steps. First, carbonization of rice husk. Second, leaching of silica from carbonized material and depositing it in the form of silica dioxide. Third, activation of a carbonaceous material during water vapor or carbon dioxide. At the first stage, carbonization of a rice husk was carried out to obtain material containing 43.1% carbon and 25% silica. The most important stage in the formation of porous structure of the material is the activation. Products were obtained by activation of carbonized product with water vapor or carbon dioxide at temperatures of 700 Celsius or 850 Celsius, with varying flow rate of activating agent and activation time. The best results were achieved by activation of carbon material with water vapor at the flow rate of 0.08 decimeter cube per minute per 500 grams of material and the temperature of 850 Celsius.
First of all, we have 2 grams of potassium carbonate. Then we get our 20 grams of rice husk by using the scale. After that, we mix the potassium carbonate with the rice husk. The resulting mixture is here. Now the mixture is ready to be heated. We put the mixture into heater and heat it in 900 Celsius degrees for 2 hours. Finally, we have the activated carbon.
The aim of the project is to determine the composition and structural characteristics of solid carbon materials obtained by heat treatment of rice husk grown in Turkmenistan. The purpose of this work is to investigate the effect of heat treatment methods on the content of carbon and silica in the carbonized products in order to predict the composition of precursor for next activation stage and to carry out the process of activation of carbon residue. Conclusion. The results obtained show that the rice husk-based activated carbon using phosphoric acid as activator can be readily used for the absorption of benzene. The absorption of activated carbon can be controlled by modification of the impregnation ratio of phosphoric acid, activation temperature, activation time, and heating rate. The optimum activation temperature is 900 Celsius, activation time is 3 hours, the impregnation ratio is 1/2.